You've probably heard that carbon dioxide is warming the Earth. But how does it work? Is it like the glass of a greenhouse? Or like an insulating blanket? Well, not entirely. The answer involves a bit of quantum mechanics. But don't worry, we'll start with a rainbow. If you look closely at sunlight separated through a prism, you'll see dark gaps where bands of color went missing. Where did they go? Before reaching our eyes, different gases absorbed those specific parts of the spectrum. For example, oxygen gas snatched up some of the dark red light, and sodium grabbed 2 bands of yellow. But why do these gases absorb specific colors of light? This is where we enter the quantum realm. Every atom and molecule has a set number of possible energy levels for its electrons. To shift its electrons from the ground state to a higher level, a molecule needs to gain a certain amount of energy. No more, no less. It gets that energy from light, which comes in more energy levels than you could count. Light consists of tiny particles called photons, and the amount of energy in each photon corresponds to its color. Red light has lower energy and longer wavelengths. Purple light has higher energy and shorter wavelengths. Sunlight offers all the photons of the rainbow, so a gas molecule can choose the photons that carry the exact amount of energy needed to shift the molecule to its next energy level. When this match is made, the photon disappears as the molecule gains its energy, and we get a small gap in our rainbow. If a photon carries too much or too little energy, the molecule has no choice but to let it fly past. This is why glass is transparent. The atoms in glass do not pair well with any of the energy levels in visible light, so the photons pass through. So which photons does carbon dioxide prefer? Where is the black line in our rainbow that explains global warming? Well, it's not there. Carbon dioxide doesn't absorb light directly from the sun. It absorbs light from a totally different celestial body, one that doesn't appear to be emitting light at all: Earth. If you're wondering why our planet doesn't seem to be glowing, it's because the Earth doesn't emit visible light. It emits infrared light. The light that our eyes can see, including all of the colors of the rainbow, is just a small part of the larger spectrum of electromagnetic radiation, which includes radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. It may seem strange to think of these things as light, but there is no fundamental difference between visible light and other electromagnetic radiation. It's the same energy, but at a higher or lower level. In fact, it's a bit presumptuous to define the term visible light by our own limitations. After all, infrared light is visible to snakes, and ultraviolet light is visible to birds. If our eyes were adapted to see light of 1900 megahertz, then a mobile phone would be a flashlight, and a cell phone tower would look like a huge lantern. Earth emits infrared radiation because every object with a temperature above absolute zero will emit light. This is called thermal radiation. The hotter an object gets, the higher frequency the light it emits. When you heat a piece of iron, it will emit more and more frequencies of infrared light, and then, at a temperature of around 450 degrees Celsius, its light will reach the visible spectrum. At first, it will look red hot, and with even more heat, it will glow white, with all of the frequencies of visible light. This is how traditional light bulbs were designed to work, and why they're so wasteful. 95% of the light they emit is invisible to our eyes. It's wasted as heat. Earth's infrared radiation would escape to space if there weren't greenhouse gas molecules in our atmosphere. Just as oxygen gas prefers the dark red photons, carbon dioxide and other greenhouse gases match with infrared photons. They provide the right amount of energy to shift the gas molecules into their higher energy level. Shortly after a carbon dioxide molecule absorbs an infrared photon, it will fall back to its previous energy level and spit a photon back out in a random direction. Some of that energy then returns to Earth's surface, causing warming. The more carbon dioxide in the atmosphere, the more likely that infrared photons will land back on Earth and change our climate.
Yeah.